So now we have seen the definition of signal space, and we've also seen a technique to create a signal space, to identify and create a basis for our signal space when we're given a certain collection of waveforms for our symbols. So now we get into the part where we actually exploit the signal space in order to achieve some of our goals in digital communications. So this is our signal space analysis. And the analysis is basically an examination of the error probability, determining the bit error rate for a given collection of signal waveforms, and to determine the strategies at the receivers. Remember, the first time I gave you the receiver structure, and now with signal space analysis, we're going to determine what that structure should be. And of course, we have to have a criteria for optimality, and we know we've already had the introductions to two criteria for optimality, the maximum likelihood and the maximum a posteriori probability. So that was our goal in starting out with giving you the structure, so that when we arrive now, when we're going to do the examination of signal space, you already have a good feeling for what exactly are these two. But we saw them for the binary case, and now we're going to generalize them with the signal space analysis. But all of this is covered in section 3.2 of the Scholar textbook. So our signal space analysis, we started in the first place, in the first example with the linear sampling receiver, by starting from the time domain expression for the received signal. So we said the received signal had a component coming from the transmitted symbol and from the additive white Gaussian noise. Now what we've done with signal space analysis is to be able to transfer this equation in the time domain into signal space, so that the received vector can be written as the received waveform can be written as a vector, and so we're going to be looking at the vector form of this same equation. So our question is, given our received vector, r of t, which one of the symbols in the constellation should we choose? So we use signal space to solve this problem. And in digital communication systems, one of m possible symbols is transmitted. At the receiver, we have this vector r, and based on that r, we have to make a determination which symbol was transmitted. So there are two criteria that we know we can do. We can try to maximize the a posteriori probability. So given the observation of r, trying to maximize the a posteriori probability, or we can maximize the likelihood. And so we're going to return to these ideas that we saw already, but now we're going to apply them to signal space. In order to do that, the first step is we have to analyze the noise, because these are all probabilities, right? We're maximizing a certain probability, and for what is the random process in this equation, it's the noise. So it's the statistics of the noise that are going to determine how to create these receiver structures. So in the previous case, when we had this, we would sample it, and the sample was a Gaussian random variable, and we went from there. So in signal space, it's a little more complicated because we have these vectors that we're working with, and vectors of random variables are of course more complex than single random variables. So let's go through the analysis of the noise so that we can apply this map and ML strategy to this vector form in signal space. So recall what these signal space representation is. We said that we take the r of t that we receive, and we break them down into a linear combination of our basis vectors, and this linear combination, the coefficients, become the elements of our vector representation. So that when I say I want to find the conditional probability of the received signal conditioned on a certain symbol being transmitted, this was the first step we did earlier in our linear sampling receiver. So I'm going to take, remember this SI, I've got a collection, S1 of t, S2 of t, all the way up to Sm of t. This is my constellation, this is my collection of symbols. Now, suppose I say, what's the probability that I would get this particular received signal if I sent this one? Now, what's the probability I would get this particular observation R of t if I sent that one? And I do this for every one of the SIs. Then I would be able to see which one I might want to choose if I wanted to maximize this probability. So just to write that in another way, we would say that would be the probability that R of t, of course, equals to SI of t plus N of t, because that is what the received vector is. And of course, if we just take this same equation and we put it now in vector form, this is what we're examining. This is what's important to us in examining our analysis. So this is the probability we want to analyze. So the noise vector, everything based on the noise vector, because the noise is the random process in this system. So I have a noise vector, which is infinitely long because the noise space is infinite dimension. And each one of the elements in this vector is determined by the inner product of the received waveform and each one of the basis vectors, one after the other. So that's just the definition of the vector space. Now we know that N of t is a Gaussian random process. We know that it's zero mean. We know that its power spectral density is flat. That means it's constant for all frequencies. It's equal to N0 or 2. Now once we know the power spectral density is flat, we have the Fourier transform relation between the power spectral density of the noise and the autocorrelation function of the noise. These are Fourier transform pairs. So if I have something that's flat in the frequency domain, that means that in the time domain it's a delta function. So I know that the autocorrelation function of the Gaussian random process, a white Gaussian random process, is just the constant level in the frequency domain, which is N0 over 2, and it's a delta function. So in the time domain, this correlation between between elements in the vector, they're only correlated if it's the same vector. So we'll come again to this, but if you recall our brief introduction to random processes, this was one relationship that we mentioned. So that means that if the noise, I guess I can recall what I mentioned then. If this is time, and this is some random process, N of t, some Gaussian random process. If I take a sample here at some time ti, t1, and another sample here at t2, the expected value of n of t1, n of t2 is 0, because they are uncorrelated. And the only time that this is non-zero is when these two times are actually equal to each other, equal just to one time. And then, of course, it's non-zero. It's the delta function. So that's just a little recall of what we looked at previously with random processes. And here I wrote it down again. The expected value of n of t and n of t plus tau. So any time that they're not equal, that there's some difference between them, some tau is not equal to 0, then the expected value of their product is 0. So this is a recap of what we know about the random process. And now what we're going to do is take these characteristics of the random process n of t and see what that has to do with the integral of r of t, of n of t multiplied by a basis vector. The first thing we can conclude is that all of these elements in the vector are Gaussian random variables, because this operation is a linear operation. And we know that any linear operation on a Gaussian random process yields another Gaussian random variable. So all these n of j's are Gaussian. So if I want to know for a Gaussian, I know that all the n of j's are Gaussian, right? And they have some mean and they have some variance. And so if I want to characterize this random random variable, this is what I need to find. What is the mean and the variance? Because I know it's Gaussian. But of course, I also need the joint probability density, because I'm not interested in just one random variable, but I'm interested in a random vector. But the first step in this process is to find out what is the mean and what is the variance. So let's start with the mean. So what is the expected value of one of these elements of the vector? So it's the expected value, and here's the definition. It's the integral, which is the inner product of the random process and the basis vector. First of all, I can interchange the order of the expectation and the integration. And once I take the expectation inside the integration, well, the basis vector is deterministic. There's nothing random about it. So it's really just the expected value of n of t. But I know that n of t, the random process, is zero mean. So the expected value of n of t is 0, which just means this integral is 0, which means that the mean for all of them is 0. I didn't specify any particular j, so we know that the mean is always 0. Now we need to find the variance. And the variance, again, is just because it's 0 mean. The variance is just the expected value of the square of the element of the vector. So I go back to the definition. A square, well, each one, it's the expected value of the product of n of j with itself. So here the j is the same. Here's a j over here too. And I have two integrals with two different variables of integration. So the next step is to say, well, the product of two integrals I can write as a double integral. So here it's the expected value of this double integral over z and t. The next step again is I'm going to interchange the order of the expectation and the integration. And so now the expectation goes on the inside. And again, once it goes to the inside, I know that the basis vector is deterministic, so it doesn't change the expectation. The expectation is only over the product of this random process. Okay, now this part is the part that's you have to think a little bit about, and you say, what is the expected value of nt and nj? Well, that is the same thing as the correlation of nt and nz, and we know that the autocorrelation function is a delta function, so that the expected value of the product of nt and nz is the autocorrelation function, and therefore it's n0 over 2, and it's the delta function of t and z. In other words, these processes are completely independent unless they are superposed on one another, unless they're essentially the same random process, in which case it's the delta function. So now we have this double integral of the delta function, t minus z, and the product of the basis function. So I can, well, first of all, maybe there's two steps here. One step is certainly I can take out the n0 over 2, that's a constant, so that comes out over here. So when I do that, taking that out, what remains is an integral over delta. Essentially what I have is an integral delta t minus z dt dz. I mean, there's other parts, but for now, let's just concentrate on this part. Well, the integral of a delta function is 0 unless t equals z is covered, in which case the integral equals 1. That's a characteristic of the delta function. So this delta function, instead of being a double integral, it collapses to a single integral, because the double integral will be 0 everywhere except that one instant when t is equal to z. And that one instant when t is equal to z means that this double integral becomes a single integral. So finally what I have is n0 over 2, the single interval of sigma j squared. But the integral of sigma j squared is 1. Why? Because this is a basis function, and this is the length of the basis function, and that is normalized to be 1. It's because we have an orthonormal basis. So we found the mean, we found the variance for individual elements of that noise vector. The last step is to find the cross-correlation or the covariance of two elements in that vector. I said that we needed the joint probability function, and the joint probability function is determined by this covariance. This is for Gaussian Gaussian random vector. So how do we calculate the covariance? It's the expected value of Ni times Nj, and now we have the hypothesis that I is not equal to j. That's why it's different from the variance. In the variance, I equal j. Now we're finding the covariance between two different elements. So very similar to the development I did previously. It's the expected value of a double integral. Now we have Ci and Cj. They're no longer the same. But the rest of my development is pretty much unchanged. I changed the order of the expectation in the integration. I look here at this element. Again, I can collapse the double integral into a single integral because I know that this expected value is a delta function. So here's the delta function is the intermediate step. And this double integral collapses to a single integral because it's only non-zero. It's only equal to 1 when t is equal to z. Therefore, I have n0 over t, and now I have the integral, not of the product of sigma j with psi j and psi I. Sorry, I've been saying sigma. That this now, what is this integral? Well, this is an orthonormal basis. So the ortho part means that the I and the j are orthogonal to one another, which means that their inner product is 0. Therefore, the covariance is equal to 0. That means that all of these elements in this noise vector, they are uncorrelated because the covariance is always 0 here. So the conclusion that we have is that these coefficients are not correlated, and that's based on the assumption of white Gaussian noise and the orthonormal basis. For Gaussian random variables, when they are uncorrelated, when this product equals 0, that also tells us that these random variables are independent. That's not true for all kinds of distributions. There are only a couple distributions for which this holds, but Gaussian is one of them. So the conclusion that they're uncorrelated is enough to tell us also that they're independent, which is very important because it lets us find the joint probability function of all of these elements. So we have the probability density of the entire vector. So our conclusion was that each one of the elements in this noise vector is 0 mean, and it has a variance of n0 over 2. So sigma squared is equal to n0 over 2. They are independent because the expected value of nj and I is equal to 0 for all I are equal to j. So now we can find the vector density, the probability density function of the vector, which is the collection of all the coefficients. So I have the total probability density of the vector. By independence, I know that it's simply the product of the probability density function of each one of the elements of the vector. So that's a general result, that if I have any vector v1, v2, and the vi independent vj, if that's true, then I have this result, that the total probability is the product of the marginal densities. The total probability density is the product of the marginal densities. So this is a general result from probability theory. Now I apply it. The independence of my particular noise vector means that the density function of the whole vector is equal to the product of each one of the densities. Now each one of the densities, I know, each one of these densities is a 0 mean Gaussian variable. So here is the density, which is for a single Gaussian random variable. So I have the same, they're not only are they independent, but they're also identically distributed. That means everyone is zero mean, everyone has the same variance of n0 over 2, or which we call sigma squared. Therefore, each one's density is the square root of 2 pi times sigma exponential, and minus nj squared divided by 2 sigma squared, but I have to sum over j equal 1 to infinity all of the elements in this vector. Now, what I'm really interested in is the conditional density. Now I have the density of the noise. Now I want to know what is the conditional density. And if you recall, for the conditional density, it's just the same thing as saying the density of the received vector r equal to a particular symbol plus the noise. Now the noise, now I have the density of the noise, so now I can write this probability density function for the received vector conditioned on a particular symbol being sent. So now let's look at this sum, this product that we have. We have taken the representation in the vector, and now I'm going to look at the element-wise product involving the elements of this vector. So I've conditioned on SI. So I have the vector SI, and this SI is going to have elements which are SI1, then SI2, SI3, and it keeps going, right? So now in the exponent, I've replaced what was nj here with rj minus I comma j. So sorry, I comma j. So you can see that the sum here is over all of the elements as I go through, and the index I is which one of the symbols that I am conditioning on. So having found the conditional distribution, I can now turn and apply our two strategies for maximum likelihood and maximum a posteriori probability. The conditional probability we found was the likelihood function. Here it is, the likelihood function. So what is the likelihood of this received signal given that it was this symbol which was transmitted? Now, before, when we looked at it, we had the scalar case. Instead of having a vector representation of the received waveform, we had one sample after a linear receiver. So there was one test statistic, a scalar, and it was conditioned on one of the M symbols being transmitted. So the one strategy would be to look at this likelihood function, this conditional probability, and just pick the symbol that gives us the largest probability when we plug them in one after the other for the particular received vector that we have. The second strategy is what we call the map, and so then we're trying to maximize the a posteriori probability, and when we maximize the a posteriori probability, we take the same likelihood function, but we apply a weighting function to it. We weight it by the a priori probability of each one of the symbols. So if one of the symbols is much more probable than other symbols, it will be weighted more heavily. And so we will shift a little bit, our decisions here will be shifted to favor a little bit more the symbols which are just more probable of being transmitted. So it's the same strategy. It's just that now our probability densities are going to be more involved because they are probability density functions of vectors rather than of scalars. Remember, this is the a priori probability, the same one we saw previously. That's not more complex because we're working with a vector, because it's just the probability of each one of those vectors. So that part is not more involved. So let's start with the map choice. So we're looking for the argument that's like which one of these j's, which one of these symbols maximizes this weighted expression for the likelihood. So the a priori probability times the likelihood function. And again, this conditional probability is just the probability that the received function is equal to the noise plus this particular transmitted symbol. Therefore, it's the same as saying we want to find which j maximizes the probability that n is equal to this r minus sj, again weighted by the a priori probability. And this probability we can find with this expression. So this is what we developed previously. So our next step is to say, first of all, that this constant is the same for all of the elements in the product, and it's also the same no matter which j we're evaluating, so we can get rid of the constant. It doesn't change the maximization. We have an exponential multiplied by a number, which is the a priori probability. And I could take the maximization of this to be the maximization of, I can take this product, which is a product of exponentials, and say, well, that's just the exponential of a summation. So this is using the result that e to the x1 times e to the x2 is just e to the x1 plus x2, right? So I just do that now for this product. So it becomes an exponential of a sum. So instead of having a massive product, I just have a sum in the exponential. Makes things look a little easier. So we'll start from that point now, and we'll continue on. We have maximization of the a priori probability times an exponential, which has got an infinite sum in it. So I can take the logarithm. The logarithm is a monotonic function, so it doesn't change the maximization. So I'm going to take the logarithm of this function, and that will give me this summation plus a logarithm of the a priori probability. So a product becomes a sum, and I need the logarithm of each one of the multiplicands. And so here I have the sum, and there I have the log of the a priori probability. I can multiply by 2 sigma squared so that I can try and isolate this summation. I'd like to have the summation alone. So I move the 2 sigma to the weighting term. Now I have a negative sign here, and I have to maximize this expression. So what I'm going to do is I'm going to change it to a minimization. I'm going to multiply the whole expression by -1. So what I'm looking for is which j, the argument, which j minimizes this sum minus this weighting function. So this is my map strategy, is to find which one of these symbols, which j, minimizes this expression. Okay, so now we're going to do a very, very big simplification. We can see now that this is an infinite sum, and infinite sums are not very attractive to us. We'd like to limit the complexity, and so now we're going to be able to do that. And the way we're going to do it is, it's because of this minimization. This minimization is going to be impacted not by all elements in this summation, but on a very small, well, a finite subset of this summation. And this argument is called the irrelevance theorem. So the theorem of irrelevance says, let's remember, the way we constructed this basis was to start with a signal space which had at most dimension m. Then we extended that basis to be able to cover any noise sample that might appear. But in doing this extension, all of the elements for k greater than n, all of those elements in the vector for each one of the symbols, no matter which symbol, no matter which j, all of the symbols have 0 for the element for k greater than n. And n is, let's just recall, n is the dimension of signal space. And n can be no greater than m, the number of symbols. So that's, the signal space fits in dimension n. So all of the elements of this long vector, S, J1, Sj2, up to Sjn, okay, these could be non-zero. But after this, it's always 0. And I can go to infinity, but they're always 0. Now, I'm trying which one is going to minimize this expression. Which one of these SJs, which one is going to minimize this expression? Well, if I look, no matter which SJ I choose, they're all going to have the same, they're all identical in these elements. So I could like break it into the sum into two parts. The sum of k equaling 1 to n, and the sum of k equaling n plus 1 to infinity. And this one would be identical no matter which j I picked. So it's not going to change the minimization. It's irrelevant. So the r, you know, it could be whatever it is. And so I'm going to get it maybe, but when I take r minus the element of s, well, the element of s is always going to be 0, so it's never going to change that minimization. So, because it does not change the minimization, I can change this sum over infinity to instead be a sum to n, just the dimension of the signal space, which is why we use signal space analysis. So another way that we can write this sum is to say it's the L2 norm, the module squared of the difference between the received signal and each one of the symbols. So again, this is the norm and the finite basis of the signal space. So in essence, what we're asking with the map choice is to minimize the distance between the received signal and each one of the transmitted symbols. So suppose I'm in 2 dimensions. Suppose these are symbol 1, symbol 2, symbol 3. Then I get some received signal, and the received signal is here, R. What this says is to calculate the 2 norm, which is essentially the distance between these two, and to pick the smallest one. However, it's not exactly to pick the smallest one because I have this weighting function. And this weighting function, suppose that I would normally say the smallest addition is S2. But suppose S3 is like really, really more probable than the other. Then it's going to sort of pull it to try and be more often S3 than it would normally be. And so that is what this weighting factor can be. So this factor is saying choose the closest. And this factor is say, hey, maybe not the closest. I know that certain ones are sent just more often, and since they're sent more often, maybe I should choose them more often. And so that is the maximum a posteriori probability criteria. So just to recap, what we have is calculate the distance, look at which one is closer, but modulo a weighting function. That's the map choice. So what is the maximum likelihood choice? Well, it's just the same as the map choice, but in the case of equal priors. Equal priors means that this number is the same no matter which j I use. So if I have equal priors, prior probability, these would all be equal to 1 over m. And so when I do my minimization over j, it wouldn't matter because no matter which j I put in here, I get 1 over m. So in that case, this weighting term essentially disappears. That's what the maximum likelihood is. So once I find the map choice, I can determine the maximum likelihood choice just by eliminating the rating term. So here we are. It's say simply choose the closest signal. So in signal space, I get a received one. Super simple. I just pick the closest one to it. Very intuitive. Why I love signal space. Now remember, this is not unlike what we saw previously in our linear sampling receiver. We also came up with something that said choose the closest, but it was to take the signal, the test statistic, and choose the one that's closest to the mean. So similar, only now we have this representation in the signal space. So signal space analysis, why do we do this? You know, if I just looked at the binary case that we examined previously, it would indeed reduce to the same math. So why did I go through all this trouble of the signal space? Well, it will facilitate an extension to multi-dimensions because we've only really been looking at this two-dimensional space, so we want to do something more general. It allows that, and it also just simplifies the math so that we do it once and it applies to all of our solution sets, as we'll see. Here's a quick example of questions from the exams. I won't go through all of the exam questions, but I can point you to them if you'd like to prepare for our exam. For instance, here is a selection of 3 waveforms in time. One is constant during the symbol interval. One is a cosine function, and one's a cosine squared function. The frequency is changed between these two. So the first question is, do these signals have equal energy? What is the average energy per symbol? And create an orthogonal basis for these 3 signals. So the first one is, do they have equal energy? Well, that's easy because the way we find out if they have equal energy is just calculate s squared of t dt for the symbol interval. In this case, 0 to 1. So we can do the math, and we find that indeed they do not have the same symbol energy. It's 1, 1/2, and 3/8. And because they're not the same, then it's important to do a calculation of what the average energy per symbol is. So we take 1/3 of the sum of these 3 and we get 5/8. And then I'll leave you to look at the problem and do for yourself to use the Gram-Schmidt process to find a basis for this signal. So to find a signal space basis. I'll give you a little hint. There is a trick you can use to not have to go through all the math in the Gram-Schmidt process if you look at the relationship, the trigonometric relationship between these 2 symbols. And finally, there's another example, it's one I mentioned previously, where there is a one-dimensional signal space with 3 symbols. And I tell you that the values for the all the parameters needed in order to calculate the map probability. So maybe it's a little early to do this problem, but it basically takes the equation for the map, which I gave you a few slides ago, and you have the numbers that you can plug in order to calculate it.